Broadcast is now starting. All attendees are in listen-only mode.
Good morning, everyone, and thank you for joining us today. My name is Justin Falkenstein, Strategic Marketing Manager at ITI, and I'll be the host for today's webinar. Today, we're excited to have you join us because we'll be discussing what's new with meshing in CADfix DX13 Service Pack 1. Before we begin, I'd like to go over a few quick items. All attendees will be muted during the duration of the presentation. If you're experiencing technical difficulties, please try refreshing your browser and logging back into the live stream. If you have any questions, feel free to enter them into the question window, and all questions will be addressed following the conclusion of today's presentation. Also, today's presentation is being recorded and will be made available by tomorrow afternoon. Today's presenter is Henry Bucklow, Product Manager and Developer at ITI. Henry graduated from Cambridge in 2005 and has been with ITI for 19 years as a developer and manager. His expertise includes feature removal, 3D medial object generation, shrink wrapping, and meshing. Since 2016, he has served as the product manager for ITI's meshing and visualization solutions, driving innovation in 3D geometry processing. And at this time, I'll turn things over to Henry. Thank you, Henry, for joining us.
Thanks very much, Justin, for the warm welcome. Can you hopefully you can see my screen, Justin?
Yep, I can see it just fine.
Excellent. Okay, brilliant. So for those of you who aren't familiar with ITI, the main bulk of ITI is based out of Milford, Ohio, where I suspect Justin is talking to you today. But I'm talking to you from the team based near Cambridge, which is International Technical Group Limited. And this is the centre where we develop CADfix. And we've been doing this for a long time. We have 45 years of geometry and mesh generation expertise that's gone into CADfix. And you may be familiar with how CADfix is used for smoothing out the reuse of CAD geometry for CAD to CAE processing and for other applications. But actually, our history, originally CADfix was developed as a mesh generation product. It was known as FAM back when the company was called FEGS Limited as a CAE pre and post processor. So we're continuing that long history today with the latest developments that we're putting into CADfix 13 Service Pack 1. Which is available on Windows and Linux. Those are the two platforms that we develop for these days at ITI. Okay, so CADfix has a range of products now under the CADfix brand. CADfix Data Exchange, or CADfix DX, is the first product that we released. And this is our tool for CAD healing, repair, defeaturing, and cleanup. So taking CAD models and making them suitable for reuse in a different process. So this might be the version of CADfix that people are most familiar. It's certainly the version that we've produced for the longest. More recently, we've been working. We've had a lot of success with a tool called CADfix PPS, which is for process plant simplification. So this is really aimed at taking large, complex equipment models for industrial equipment and simplifying them drastically for use in plant layout software. So for laying out factories or ships or oil rigs, where the very small details in these very complex equipment models are not required. So CADfix PPS can do this automatically. I'm also the product manager for CADfix Viz, which is our tool for visualization for VR, AR, and mixed reality. And this has some overlap with CADfix Mesh. It's primarily focused on generating simplified faceted representations of models suitable for import into these virtual reality systems. And we have a free tool called CADfix STL, which is for generating provides a simplified interface for generating faceted models for export to STL from STEP and IGES. So a few of the things that you see today in our CADfix Mesh product can be previewed in this CADfix STL. It's slightly old now, so all the latest bits and pieces that I'll show you won't be available. And the other product that I'm not going to talk about today is CADfix Morph. This is our tool for morphing performing NURBS morphing. So if you have a mesh and a deformed version of that mesh that represents a deformation field, you can import this into CADfix and you can deform your model to match the deformations on that mesh. And that's done by morphing the underlying NURBS geometry, so it gives you a very high quality result afterwards, suitable for import back into a CAD or PLM system. But today I'm going to talk to you about CADfix Mesh. This is our tool for advanced mesh generation. So we're going to talk across a few different topics here. One of the big problems that often trips up mesh generation is CAD. So we'll talk a little bit about what CADfix Mesh can provide you for simplifying or for fixing your problems before we get to the mesh generation stage. And then we've split the mesh generation topic into STL or surface meshing and CAE or volume meshing. We'll talk a little bit about mesh sizing as well. So we've got some advanced options there that we'll detail a little bit more, and a brief preview of hex meshing. One of the strengths that we have is automation. So we'll talk about how CADfix Mesh can be integrated into other workflows through our various APIs, and then we'll summarize at the end. So as I said, there are two strands to this webinar. We've divided it into STL or surface meshing. So this is mesh generation for AR or VR, so generating very coarse visualization meshes, or meshing that we're doing to generate a geometric proxy for another tool, so for import into CFD tools like OpenFoam, for example. And we've described this as STL meshing because this is it's the most common format that we generate, that we export to for surface meshes. But there's a wide array of formats that we provide export to, which we'll talk about at the end. And then the other strand of this webinar is going to be CAE mesh generation. So this is linear and quadratic tech meshing for finite element analysis, for example, and hex meshing, of course, falls into this category as well. But both of these routes are built on the same engine. They're both built on CADfix and its tolerant geometry kernel, and they have access to all of the same CAD repair, defeaturing, and sizing and automation options. So a quick demonstration then of what meshing looks like in CADfix. This is a demonstration of STL mesh generation from start to finish on a simple model. You can see we're importing the model here, and I think we're just going to have a show quickly what it looks like on the screen. So it's a mock-up. A mock-up CAD model. It's not a real F1 car, but some of the same characteristics carry over. So we're going to generate a surface mesh on this model. So it's going to go out to STL. You can see the various options we've got there, and we can change the mesh style in this export setting. So we're going to stick with the defaults and generate a mesh suitable for visualization using this minimal mesh preset that we have in the top left. So this is generating triangles with no regard for triangle shape, just attempting to produce a minimal set of triangles that will represent the geometry that can be exported to a visualization system, for example. And you can see we've got some very long, skinny triangles in there. It's a relatively coarse representation. The sizing controls, sizing defaults that we have are fairly coarse. If we reduce the facet length, then that will change the aspect ratio of some of these triangles. So it'll reduce some of the long, skinny triangles that we could see before. Now those have been brought down in size. We see this as something that people often want for import into tools such as OpenFoam for use with snappy hex mesh. They'd like to limit the aspect ratio of triangles, which this length option allows you to do. So yeah, that's an example mesh generated in there. This is all real time, by the way. So these meshes are. This video is not it's not sped up. These is the time it takes to generate these meshes. And yeah, finally we've imported the model. It didn't require any repair, so we're just exporting it directly. Okay. And that's the end of that little demonstration. So that's the first strand. for STL mesh generation, and I'm going to show a quick preview of the other strand for CAE mesh generation as well. So this is another import of a more complex part this time. You can see we've got this complex casting, and it has a set of very complicated fillets. It's got a lot of very narrow faces, very complex topology that can cause problems potentially for mesh generation, and can also impose constraints on the mesh generator. So if the mesh generator is forced to put elements into some of those very narrow faces, it can affect mesh sizing and it can affect mesh quality. So again, we're going to export this to mesh, and this time we're going to use the TET-mesh preset. So we're leaving this as linear TET-mesh, as a linear TET-mesh for this first run, and running the generation now. This one, I believe, is a little bit accelerated, just to keep the webinar moving along. But if you look in the bottom left, it'll tell you how long the process takes. So it's a little under 3 minutes to generate 1.5 million first-order tetrahedra on this model. So if we zoom in on some of the complicated topology on this model, we'll see that the mesh generator has actually been allowed to collapse out some of the geometry internally. So it's not fully respecting all of those very narrow faces, all of that very complex topology. Instead, there's a simplified version of the topology that you're seeing overlaid on here. So the mesh sizing has not been compromised by some of these very narrow faces, some of this very complex topology. And that's helped to increase the overall mesh quality and keep the mesh size appropriate to the model, much closer to the geometric constraints that we're trying to satisfy. And then I think as a final step on this model, we're going to regenerate it with quadratic TETs using the same settings. So it's going to be a very similar mesh, a slightly lower element count, and you can see the curvature of the elements visible on there, just to indicate that these are quadratic rather than a linear tetrahedron we've generated in this instance. So yeah, that's the overall process on this model. I think that's the end of this video. Okay, so with those two quick run-throughs done, we can return back to the beginning of the process, where we get a CAD model imported, and we're tasked with generating a mesh. One of the hurdles that people have for mesh generation is the quality of the CAD that they're given. If they have features like the very narrow topology, very narrow faces that we saw in the previous model, or large gaps between edges and surface geometry, or very short edges, these kinds of common defects can cause problems for mesh generators. CADfix, of course, has a long history of repairing such models, and as such we have a geometry kernel we've developed over the years that's very tolerant to these common CAD defects, and this same geometry kernel is used to build our mesh generators. So the models that you saw there didn't have any repair beforehand because the mesh generator was tolerant to the defects, the problems that were present in that CAD model, and that speeds up the overall process. However, if we have bigger problems with the CAD model, we do have this large library of CAD cleanup, CAD repair, healing tools that we have available within CADfix to repair some of these models. So if you have a legacy IGES model, for example, coming in and it needs a significant amount of repair, then we have the full CADfix toolset available to do that. So the CADfix, you'll have seen in the previous, briefly in the previous video, that we have these steps in the CADfix wizard. We have the repair step to correct topological problems in the model and make a solid. So this fixes the sorts of problems you see on the right-hand side in these images. I'll talk a bit in a second about the transform options that we have to simplify these models. And then finally, there's a prepare step that can adapt models for mesh generation to just smooth out mesh generation process. So we have a large number of transform options available. I'm not going to talk through these in great depth, but we have the ability in either interactively or in batch to remove holes, protrusions, lettering, fillets, chamfers, or perform mid-surfacing of certain types of bodies automatically during the batch process. So if you want to bring the model in, perform some defeaturing, and then generate some mesh as part of your workflow, that can all be done via the CADfix batch process. There's some examples of these. As I say, I'm not going to do them all, but common ones: fillet removal. So this is an example from our tutorials on fillet removal. One click to find the fillets, a second click to remove them. Lettering removal is very similar. We have it's one click to find the lettering, second click to remove it. And mid-surfacing, one of the things we've added in CADfix 13 Service Pack 1, and if you joined the previous webinar, then you've seen my colleague Steve present a little bit more on this. We have mid-surfacing operations, so we can detect bodies that we can mid-surface, again with one click for this simple extrusion, and then a second click to convert it. And these mid-surfaces can be meshed either. Here I've used equilateral triangles, so I've used one of the meshing presets that we have to mesh this, or if you want a more structured mesh, then you can mesh these with structured quads, or the faces are four-sided by construction. So I have a recipe for doing this that I've used, and we'll talk a bit about recipes later. Another common problem that we get with the CAD models is imprinting. So if you import a multi-body CAD model, you may have multiple parts in contact, and you would typically want to be able to have a common boundary condition between those parts, which means that you have to have common boundaries to the mesh in those regions. So for example, here we've got a suspension linkage, and there's this circlip here, which is being held in contact with this piece of linkage. And we want to make sure that there's a common face between those two bodies, so that we can have a mesh imposed in that area. And imprinting finds bodies where that are in contact, where there is no a common face in those areas, and scratches a face into here so that we can have a common area for a boundary condition. And we have a linear version of this, which you see here. There's a cyclic version as well for rotating components. I have a quick video now which will demonstrate this, I think, in a little bit more detail. I think it's the same model, but it hopefully might illustrate a bit better what I'm talking about. So again, this is a simple this is a suspension linkage model. It's a multi-body model, so you can see we've got a lot of components all being held in contact with one another. So presumably these are going to need to have some relationship in the simulation, with some boundary conditions imposed between the different pieces. So if we select some pieces of the suspension linkage, we can simplify this picture a little bit. I think we're going to generate a mesh very simply without performing any imprinting, just to show what happens. So again, we're going to generate a mesh, look at the export settings, and this time it's going to be a surface mesh that we're generating using equilateral triangles. Again, the mesh is generated. That's real time, so that's 4 seconds to generate that mesh. And if we hide the body, you can see that there's no relationship. There's no between these bodies as it stands to start off with. The body's meshed as if the circlip is not present, because there's no feature on this suspension linkage that corresponds to the circlip. So if we undo that, we can apply our imprinting tool to detect those bodies in contact and add the missing topology. So we have some controls over what it means for a body to be in contact, so a maximum gap and a maximum draft angle. This means that the contact detection is somewhat more robust than you might find from a CAD system that would try and do this via a Boolean approach. and we can tolerate a certain amount of gap between these bodies, so they don't have to be absolutely perfectly in contact. Now you can see the contacting faces are highlighted in red, so it lets you check that the contact patch is what you, the contacting faces are what you expect it to be, or what you expect them to be. And then if we hit the fix button, it will scratch the faces to add the matching topology so that we've got the imprint of that circlip on the suspension linkage. And there's the new face scratched into that linkage. So now we should be able to go and generate a mesh on this body, and we should see that the mesh now features, now has triangles that follow the shape of that circlip on the linkage, and those triangles could be assigned a boundary condition that would be suitable for simulating that contact. So if we hide that, then yeah, we see the imprint there. So that should simplify generation of meshes for more complex assemblies by letting you build a consistent mesh more easily across these larger assemblies. Okay, so with the preparation out of the way, we'll move on to the first strand of mesh generation itself. So we're calling this STL meshing, but it's surface meshing. STL just being the most common export format for these kinds of surface meshes. So as I mentioned earlier, we have three main uses for these STL meshes. Visualization, where our target is to generate as few triangles as possible to represent the geometry. We don't care at all about the triangle shape. It just has to be as lightweight as we can manage to reduce the load on the visualization software. The second aspect is generation of proxy geometry. So there are several mesh generation tools out there which require a proxy geometry as their input. So typically they would accept an STL file, which they then generate a mesh on top of, but they have their own requirements on that STL file. So for starters, they require a certain geometric fidelity. So you might require that the triangles that are generated are within a certain distance of the CAD geometry, but also they might have requirements on triangle shape, typically to make sure that normals can be correctly recovered. So we have tools for generating these proxy geometries where we have some control over the regularity of the mesh alongside the accuracy. And then the third option, or the third use, sorry, is for CA simulation. So in this instance, we're interested in equilateral triangles. We absolutely need accuracy to the geometry, but we also need smooth sizing. So we want to make sure that the sizing of these equilateral triangles doesn't vary too fast in order to provide a useful simulation mesh. So we can do all of these three options through in this STL strand. We have, you'll have seen already that we have some basic sizing parameters that we use across most of our meshes. So we like our meshes to be driven by the geometry. And there are two primary sizing rules that we use to drive our mesh size based on the geometry of the model. So the element sag is the maximum distance between each of the elements that we generate and the underlying CAD geometry. So this is a measure of the accuracy of the mesh. And we have turn, which is the maximum surface normal deviation across the element. So this is nice because it's scale independent. It sets the number of divisions that you would have around a circle, for example. So this can be very useful for visualization meshes where you want to make sure that the characteristics of the object are captured and don't care so much about accuracy, about a specific accuracy in terms of a numeric value. We also showed very briefly earlier that we don't always respect the topology of the supplied CAD model. So we permit the mesh generator to ignore narrow faces, slivers, in order to improve the mesh quality and to avoid having to have very, very small elements in particular areas. So here's another example of the same thing. This is the driver CFD test case, automotive test case. And you can see, look, zooming in on this headlight area, again, we've got an area of very complex fillet topology. And these very complex fillets constrain the mesh, or they can be allowed to constrain the mesh. So as you can see in the top picture here, the mesh is being constrained to these fillets. We've got some very small element edges in these areas. But we have a parameter which we call the collapse size. We have a default setting for this, but it can be manually overridden inside this advanced options tab. And this collapse size here tells the mesh generator that it's allowed to collapse elements that are smaller than that size, regardless of whether the elements come from different faces, for example. So this is a larger collapse size that's been applied to this area of the headlight, and as you can see, the overall mesh density has been reduced a little bit, and the quality of the triangles that's been generated has been improved by allowing these very, very small elements to be collapsed out. Alongside our triangle mesh generator and our tetrahedral mesh generator, we also have a quad dominant mesh generator available. So as an example here on this Formula One car, you can see a direct comparison of our triangle mesh generator and the quad dominant mesh in isotropic mode. So it's trying to generate elements that are approximately square. And then on the next page, we have something that looks a little bit more aerodynamic, where we have, again, a comparison between our triangle mesh generator and the same quad dominant mesh generator, but now it's been allowed a bit of anisotropy. So we're allowing a maximum of anisotropy of 5:1. So you can see around the leading edge here, we've got some anisotropy being allowed in these elements. They're turning into rectangles that are longer in this direction and thinner in this direction. And this again has been tweaked using a mesh recipe, which is the thing that I'll talk about a little bit later. So to put all that together, here's a demonstration of another demonstration of STL mesh generation on this driver test case. You can see it's set up as a CFD test case, so the wheels have been blocked off and the floor underneath as well. We're going to again export this to STL as our choice of file format. And this model doesn't require any repair. We switch off those various CADfix stages just to keep things quick. And again, we're going to mesh this with the defaults. This video again is running in real time, so yeah, that's 4 seconds to generate the mesh, or the minimal mesh on this model. And again, it's a minimal mesh, the sort of thing you might use for a visualization. So we've got no control over the triangle shapes. And when you saw underneath the car, it's got some very large elements on there. If we zoom in on this area with this very complex topology, you can see that there are some small elements in here that have been imposed by that topology. So our default collapse size is not large enough to remove those. We can increase that if we want a coarser mesh still. So if we want to further simplify the geometry, so that's what the mesh looks like with that increased collapse size. But if we go and look at the door handle, then that's going to show that this visualization is relatively coarse. So you can see we've set a sag of 2 millimeters and a turn of 30 degrees. So this is a relatively coarse, simple mesh. So we would probably want to, we may want to represent the geometry a little bit finer than this. So if I halve the turn angle and we zoom back in on the door handle, we'll see that the fillets around the door handle are now somewhat better represented. The number of elements across those areas has increased a little bit. But if we were using this as a proxy mesh for a geometry for a mesh generator. We might not like these very large triangles underneath. We might want to simplify. We might want to divide those up. So if we set a facet length of 100, now you can see the sort of background size on this model has been reduced. We've got rid of some of those very long, skinny triangles that we had before. So this might be a little bit more suitable. But if we probably a facet sag of 2 millimeters is probably a bit too big still for that sort of geometry proxy. So we'd probably prefer something like 0.1 millimeters. So if we generate the mesh for that, so this is the more complex one, but still only takes 5 seconds to generate the mesh. And you can see now we've got something that's got a pretty good fidelity to the original CAD. Just give you a quick view of what it looks like over the whole model, and yeah, it looks reasonable. Just to give you an idea of how the curvature is captured, I think we'll just look at the silhouette of this headlight, so you can see the curvature of these areas is pretty well captured by this geometry proxy. So we have also have some geometry, some facet quality checks that can be imposed. So we can turn those on. There are multiple different tests available. So you can test for several different geometric conditions on the facets that we generate. So those will be checked during export. In fact, one of them was already being checked. The fold option was already enabled, so that was being checked during export already. And then finally, we can export this geometry. And yeah, you can see the quality checks have been run. No quality failures were found. Okay. So moving on from STL generation, I'm going to talk about our CAE mesh generation thread. So this is our volume meshing technology. So linear TETs, quadratic TETs, and we have a hex and a mixed hex TET mesh generation capability. But unfortunately, there isn't really time to discuss that in too much detail in this webinar. So that's going to be postponed. We're going to have a second webinar focusing solely on hex meshing that's coming soon. So the CAE meshing is governed by the same sizing that we saw for STL meshing primarily. So we use the same sag, turn, maximum length geometry-based controls that we saw in the STL generation section. But it also gives some additional controls as well. One of these being expansion rate. So this is the control over how smooth the mesh is. So we require that the elements are at most 1.5 times, an element is at most 1.5 times the size of its neighbor. And you can see the impact of this on these two meshes. The left-hand one is the default of 1.5. The right-hand one is allowing a much bigger rate of 5:1 element growth. And you can see the impact on the mesh quality histogram, that the area ratios, this is a histogram of area ratio if it's too small to read, that the worse area ratios are now much more abundant in this. And we're generating far fewer elements as well. So this is one of the additional controls that we provide for CAE mesh generation. We also have a mesh sizing control we call auto refinement. So this sets the minimum number of elements that we want across a face. So for example, if we take these narrow bands that have been cut into this landing gear, by default, just following the sag, turn, and maximum length sizing, we're only getting one element across this narrow band. However, we can set auto refine to 4 on here, and this will measure the thickness of this face and ensure that the boundaries, that the mesh size along the edges and in the interior is such that we get 4 equilateral elements across this face. So this can be quite useful for ensuring good quality across thin objects that wouldn't otherwise get sufficient refinement. One of the difficulties that we have observed in generating robust tet meshes on objects is handling of thin regions, and in particular regions where the meshes could self-intersect if the sizing is not done appropriately. So this is one of our test models. It's a bottle with cap, and we can see here that the outer face of the cap comes very, very close to where the threads of the bottle have been cut into it. It has this very narrow gap in this region, and one of the potential problems is that if we're generating a relatively coarse mesh on this object, we could allow a mesh size on this outer face that's large enough such that it will cut through the bottle cap, cut through the threads here, and produce a self-intersecting mesh. So we have some technology to identify these narrow gaps and identify whether there's a risk of self-intersection between the inner and outer parts of this body, and this then forces the outer surface to be automatically refined to avoid that intersection. So I have an example here. You can see a simple sump type model, and we're going to generate a CAE mesh again on this. So selecting mesh, and if we switching off these options again, we don't need to repair this model. It's already suitable for meshing, and we're just going to generate a quadratic mesh on this. Again, this one is this video is a little bit sped up for the meshing step. You can see it's I think 36 seconds to generate the mesh on here. And if I cut through, we can see whether the potential self-intersection is, and that the outer face has been refined sufficient that we doesn't touch the inner face on this object. Now, if we change the meshing settings, that behavior is still retained. So we could set a very large sag, so 10mm sag, a large facet length, so that's not constraining anything, and remesh this. And it doesn't matter what you set those settings to, the potential self-intersection is detected and avoided by ensuring that the geometry is suitably refined. So this is one of the things that helps us to achieve a good level of robustness in our tet meshing today, making sure that you don't have to go in and make these decisions yourself by examining potential problems in the geometry, but instead the tool can detect it directly. So again, if we zoom in on that corner, then you can see that the refinement on this fillet has hardly changed, even though the overall mesh density has decreased, because it can't be allowed to decrease any further without causing a self-intersection in the model. Okay. Another sizing tool that we have for improving robustness is size propagation. So this kicks in where you have a curved object that requires relatively dense mesh next to a relatively flat region where the mesh would ordinarily be relatively large, falling back to the background size. What happens is we detect this mismatch. We detect that this curved object is in close proximity to something that's flat, and we propagate the size from the dense mesh onto the sparse mesh in order to ensure that the sizes are compatible. So this is an example on a more realistic model where, again, we've got a region of a very dense mesh down here that's been propagated up to ensure that we get a suitably dense mesh up here. As this propagation goes outwards, the size is allowed to increase following our expansion rate that we discussed earlier. So further things that we do to improve robustness for quadratic tets is we detect invalid quadratic triangles, and we ensure that those are optimized to correct any problems with the quadratic triangles. So we make sure that there's no invalid quadratic triangles being passed to the mesh generator. Our sag and turn values, the sizing that we saw earlier, applies to the quadratic triangles, not the linear ones. So by default, we double the turn angle that we use compared to the linear triangles because of the increased approximation power that you get from the quadratic triangles. And we require fewer of these triangles to meet the given sag as well, because we take this curvature into account. When we place the mid-side nodes for the final quadratic tetrahedra, they're adjusted to make sure that we get a positive Jacobian, or at least we have an option that's on by default that allows this. This gives us a more robust meshing process because these negative Jacobians can be easily corrected. This can be switched off if required. We also report where the changes were made. We give a visual indication of how much the mid-side nodes were required to move to give some reassurance that the geometry hasn't been altered too much. Okay, so another quick demonstration of how this all hangs together. This time we've got an engine block model, and we're going to show a couple of different quadratic meshes on this model and how the parameters affect it. So yeah, it's got a reasonable complexity. So a lot of small details on this thing. Again, we're going to export this to mesh. And we're going to disable the various repair transform options because they're not necessary on this. The mesh generator can cope with any geometric defects that are present. So we're going to use the defaults, generate a quadratic mesh. This one is sped up. I think this is going to take about 4 minutes to generate the mesh. If you look in the bottom left-hand corner again, it'll show the statistics. Yeah, so 4 minutes, just over 1 million quadratic tets, and you can see the curvature of those tets on some of these large areas that they're being curved to represent the geometry. So we do have some mesh quality metrics that we can apply. In this case, we're going to look at the Jacobian. That's one of the, scale Jacobian, sorry, is one of the important mesh quality metrics. So if I click on that, we get a histogram up. The Jacobians are all positive, as we'd expect. So we'll zoom in the positive range so that we can then get a better assessment of the distribution. We do have a few elements in there that are relatively small Jacobians. Perhaps we're not very happy with those, so we can display those on the screen, get an idea for where those are. And if we were working a bit more in depth, we could assess those to see what controls we can apply to remove those. In this instance, we're going to reduce the facet length so that we've got less overall variation in the mesh size on this model. So set that and remesh. Again, sped up, but it's going to take about 4 minutes. 4 minutes time. This is running on my. I meshed these on my laptop, so it's not a big workstation. Yeah, about 4 minutes to generate that. Again, 1.1 million tets this time. And yeah, that's the result. You can see the increased density caused by decreasing the facet length. And yeah, that's the end. So you've seen some sizing ability to customize sizing that's applied to meshes, but we do have a more complete customization option that lets you set all of the different mesh styles and mesh sizing options, which we call mesh recipes. So if you click on this, we click on this chef's hat option, we get the access to the mesh recipes tool, and this has a set of predefined recipes that you can use as templates to play with. There are a bunch of recipes that reflect the presets we have up here. So the minimal triangles reflects this left-hand option, for example. But then if you click on the settings dialog here, we get into the mesh recipe editor. And this provides a GUI for directly manipulating the sizing rules and for modifying mesh styles as well. So you can set different mesh styles and different entities. You can set different sizing rules on different sets of entities. And these can be these sets of rules, this recipe can be loaded and saved to a file. And when it comes to then generating the mesh, these rules are run from top to bottom. So we've got a quick example of what this looks like in practice. So again, we've got our Formula One car, and just to indicate that it has some labels on here. So in particular, the wheels have a label called wheel, so they can be found during mesh generation. Again, we're exporting to STL, bring up the settings. This time we're going to go to the recipe preset instead. And we're going to start from the minimal triangles predefined recipe and load the settings so we can see what that looks like. If I click the surface mesh button, we'll get another preview of what this mesh is. So again, this is a minimal mesh, you can see. But if we enable this sizing rule for maximum length, we can then tweak that and get our apply maximum length to reduce the aspect ratio of some of these triangles again, so you can see the effect that has. But we can also use this assistant, and this is a preview really of a tool that's coming in the next release, but this will be present in our Service Pack 2 release. We can request the assistant to set a maximum length on a particular area using natural language, and it will propose a new recipe that incorporates that rule. So you can see that here, it's added an extra rule for the wheel. This can be edited, so we have a more conventional editor as well for these things. So you can see this is we have a templated editor for finding faces with a particular label, for example. Then if we generate the mesh, you'll see that it will reduce the mesh size in those areas. Okay. And then we can save the recipe file. So it's saved to a .mrp file. It's actually a JSON file, so it can be edited in a text editor as well if you want to fully customize it. We have multiple options for integrating CADfix into your workflow. So we have a batch process that I've talked about a little bit. So we have a CWC file that saves all of your settings, and you can use that in an automated workflow. We have a tool called libcdfx that will generate a CWC for you and let you integrate CADfix into your C program. We provide a cloud API. We have a REST API that will run CADfix batch as a service. And if you want to get down into the fine details, then we have our CADfix API, our SDK with bindings to multiple languages for getting access to the kernel itself. We have a big range of export formats. I'm not going to read all of these out directly, but you can take a look and see if the format you're looking for is there. As I mentioned earlier, we develop for Windows and Linux, so it's Windows 10, 11, Linux, Red Hat Enterprise Linux 8 is our primary Linux platform, and we have a cloud service as well. So as I mentioned very briefly, hex meshing, I'm not going to dwell on this too much because we have a whole webinar dedicated to it, but we have a set of tools available in CADfix 13 Service Pack 1 for performing semi-automatic splitting of bodies for high quality hex meshing. So we have a range of tools, sort of power tools that can automatically split models with a little bit of user guidance, using technologies like 3D medial axis and crossfield to produce suitable topologies without having to draw all of your splits by hand. So yeah, as a sort of preview of some of what some of these things look like, you can see on the screen some of the sort of kinds of cuts that we can make automatically. But my colleague Robin will be covering this on the 12th of March. I very much encourage you to join that webinar. I think it's a fabulous set of tools, and it's all driven by the same mesh generation engine in the end for then generating meshes on those on these blocks, these partitions that we make. So it has the same recipe editor, the same controls over mesh generation. So in summary, we've built a robust mesh generator, tolerant mesh generator on the CADfix platform. We have two main strands for mesh generation. So STL meshing for visualization or proxy geometry, CAE meshing, generating TET meshes for FEA or similar analysis. We have a highly controllable mesh generation process using either geometry-based sizing, which is simple to use, or our mesh recipes for full customization. And we have multiple options for fitting this into your workflows. Thank you very, very much for listening to me talk all this time. I'm hoping there's a bit of time for some questions.
Yes, thank you very much, Henry, for that great presentation and demo. At this time, if there are any questions, please feel free to enter them into the Q&A window now. And it looks like we do already have a few. First one is, we receive complex CAD parasolid kernel geometries for additively manufactured parts. Quality is relatively poor with mismatched corners and edges. Can CADfix repair such geometries automatically and export to step format or to Creo Granite format?
So that was importing parasolid files with potential quality problems. So yes, I mean, so CADfix DX, the CADfix Data Exchange, that's the kind of thing that it excels at. We have options for merging out poor quality geometry to stitch it into something that would be useful. Of course, it's hard to say for certain without seeing the particular models, but I believe we'd be very happy to take a look at those models and help you find out if CADfix would be able to help you. But yes, that's exactly the kind of workflow that CADfix Data Exchange is very good at.
Thank you. Next one is, when you import a multi-bodies design and you want to generate a TET mesh, is the imprinting process done automatically or manually?
So the imprinting tool has to be run. So we don't automatically perform the imprinting if it's not requested. But the imprinting tool works as you saw in the quick demo. It's a one-button press to run the to run the imprint, and there are a couple of variations of that as well. So whether you want the faces that are imprinted to be shared between the bodies or not is again one of the things that we can control. But it's still a one-button press. It is something that can be done in batch as well. So if you're running a batch process, you don't want to if you're not running interactive, then imprinting can be run as part of that batch process and configured through the CADfix CWC file.
Great, thank you. Next one, how parallel is your mesh generator? Will it scale for bigger models?
So the TET meshing part of the mesh generator is parallel per body. So for large multi-body models, then we mesh each of the pieces in parallel through the TET mesher. There are some parallel pieces to our surface mesher, so for our STL meshing, but by and large, it's a relatively rapid single-threaded process.
Okay, thank you. Can you force small features to be meshed if they get collapsed out?
Yes, so we saw a couple of instances of the collapse tolerance being applied earlier to remove small features. So one option is to reduce that collapse tolerance, so we can drive that down. But also people may have certain areas where they want features to be preserved and other areas where they don't. And for that, if you go into the mesh recipe editor, then you can find the collapse step that happens as part of the recipe, and you can lock certain pieces of geometry in there, and then save that in your custom as a custom recipe that you can use to protect and preserve certain areas.
Thank you. Can you mesh just the wetted surfaces of an assembly?
Yes. So if we have a multi-body assembly, we can use the imprinting tool or a version of the imprinting tool which we call join bodies. Join bodies will combine the bodies of the assembly together into a single solid. It's not it uses the same tolerant approach that the imprinting uses. So it allows a certain amount of gap between the bodies. So it's typically more forgiving than a union that you might attempt in a CAD package. And then once the bodies are joined, you can mesh the outer wetted surfaces of those bodies.
Great, thank you. And that appears to be all the questions we have at the moment. Once again, Henry, I want to thank you for the presentation. And as a reminder, a recording of this presentation will be made available by tomorrow. If there are any other questions in the meantime, please feel free to reach out to us directly. You can visit us at www.itiglobal.com, or you can reach out to us through email at info@itiglobal.com. Again, thank you everyone for joining us. We hope you found this information valuable, and we look forward to seeing you in our next webinar. Thank you and have a great day.